Hello. So this lecture I'm going to make various comments about how to handle this logical notation and the quantifiers, so the for all and there exist symbols. So the lecture is going to be a series of remarks, and I'm going to start with some remarks about statements of the form if P then Q, or equivalently P implies Q. Right. So these are probably the most common types of statements that you'll see coming up all over the place. But they might appear differently sometimes. So there's lots of different phrases that essentially mean the same thing and that logically are equivalent to each other. So the first remark I'll make is that the following, I'm going to list a few different ways of saying the same thing, mean the same. So we could say if P then Q. We could say P implies Q. We could say P only if Q. We could say whenever P holds, then Q holds. We could say P is sufficient for Q. Or we could say Q is necessary for P. These all just mean that whenever P is true, then Q is also true. Some of these you might just need to think about to check that you think that they're equivalent. At least logically, the way that we use them mathematically, these phrases are all identical. In everyday English, they have maybe slightly subtle differences, and I'll mention that in a second. But mathematically, they're the same. Another way that you could say it, which I think I'll put on the next line because it won't fit, is to say if Q is not true, then P is not true. That's called the contrapositive. It's saying exactly the same thing, right? If Q is not true, then P is not true. You may just need to think about that for a second. That's equivalent to saying if P is true, then Q is true. So there's basically two ways, or two broad ways, that you go about proving statements like this. So I'll say, to prove such a statement, you're either going to start by supposing P is true and show that Q is true, which you might be able to do directly, or you might have to do something clever in that argument, or you prove the contrapositive, so you suppose that Q is not true and show that P is not true. Or we suppose Q is not true and show that that requires that P is not true. Okay. I'll just make a comment about the contrapositive because it's a slightly confusing word. So note that the contrapositive is not the same as the converse. So the converse of if P then Q is if Q then P, which is a completely different statement. So the converse would be if Q then P, or equivalently Q implies P. That's going the other way. So if you remember, the example that we gave when we introduced this notation was P is the statement N is 2, and Q is the statement N is even. And in that case, P implied Q, but Q does not imply P. So P implies Q is true, but the converse Q implies P is not true in that case. So the converse is a completely different statement, whereas the contrapositive is just another way of saying the same statement. So maybe I'll just emphasize that the converse is a different statement altogether. Okay, if we wanted to disprove a statement like this, so we want to disprove that if P then Q, then it means that we need to find at least some circumstance under which P is true and Q is false. So to disprove a statement like this, we need to find some circumstance under which P is true and Q is not true. Okay, and then the next remark that I want to make is about the difference between the way that we use these phrases mathematically and the way that they're used in normal English. So in normal English, if I say if P then Q, then I would tend to imply that P being true had something to do with Q being true. So I would imply that there's some causality. So I might say something like, if you had not stayed up so late last night, then you would be more awake this morning. I'm implying that there's some causality between the P and the Q. But in maths, that's not the case. So there does not need to be any connection between them. We're simply saying that if P is true, then Q is true. Right. So I'm going to say here that no causality is implied by saying if P then Q. And even if we say P implies Q, we're using that to mean the same thing. So even if we say P implies Q mathematically, we don't mean implies in the way that we usually imply it in English. Right. So I could make a statement such as, if my name is Ian, then you are studying for a maths degree. And unless for some bizarre reason you're watching this video and you're not studying for a maths degree, then that is a true statement. My name is Ian. So the P is true and the Q is true. But there's obviously no connection between the fact that my name is Ian and the fact that you are studying for a maths degree. But mathematically, if P then Q, if my name is Ian then you are studying for a maths degree, is a true statement. Right? Even though in normal English you wouldn't think that that's a true statement because there's no causality. Right? So having said that, in most of the time that we're actually going to write these kind of things in maths, there will be some causality because that's the way that these statements are going to be useful. But in order to say that this statement is true, there doesn't need to be any causality. Okay. On the other hand, I could make a statement like, if my name is Richard, then your name is Ariadne. That statement would be true, even if your name does not happen to be Ariadne. Because in order for a statement, if P then Q, to be true, we simply need that whenever P is true, Q is true. So in that case, the statement P, which my name is Richard, is not true. It's never true. And so it actually doesn't matter what we say after that. The whole of the statement, if P then Q, is still going to be true. Right? So that's a little bit confusing. If you make a statement like that where the P is never true, it's a completely useless statement. And it's called vacuously true. So I'll just make a comment here that if the P is never true, the statement if P then Q is called vacuously true. And as I say, it's it's a useless statement. And so you wouldn't tend to use that in a mathematical argument. But it is possible that you might include such statements almost by accident. So you might say something like, if X is in a set S, then some property holds. And then you might later on discover that the set S is actually empty. So then your statement has not really said anything, because the P, X is in S, in that case was never true because there are no elements in S. So you can accidentally and perfectly reasonably end up writing down statements that are vacuously true. Okay, so some of these things can be a bit confusing, and what's mathematically correct can sound like strange English. So there's a question on the problem sheet which asks about various statements to do with the natural numbers that will get you to think carefully about this. Okay, so I want to make one more remark about these types of statements, and that's about the use of this arrow to mean implies. So I want to say, don't mix and match if, then, and the arrow. So you can't write things like, if x is equal to minus 1, then x squared is equal to 1. Right, what I just said was okay, but what I wrote was not okay, because the arrow here replaces both the if and the then. So here I've tried to use it in a way that's it's sort of replacing then. So this line should be read as, if x equals minus 1 implies x squared equals 1, and then I would expect that there should be a then, something else, right? And in fact, since this statement, x equals minus 1 implies x squared is equal to 1, is something that's always true, then actually this part of this sentence is not going to serve any purpose at all. So that if you use the arrow, it's standing for both the if and the then, and don't kind of confuse the notation, because you'll write things that don't make sense. Some people use this arrow to connect sort of almost every line of working in a bit of algebra. And if you're working through lots of algebra, then it usually is true that one line sort of implies the next line. But I would suggest that you don't use the arrow to do that kind of thing, and reserve it for more sort of concise statements. And you'll see examples of me doing this. I do occasionally write arrow to connect lines of working. But yeah, I'd suggest that you don't do that. And to be honest, you don't really need to. So for instance, if you wrote something like, so this is just an example of doing some algebra. Let's suppose we're solving a quadratic equation. So we're solving that. Right, so we're going to factorize it. So that's equivalent to that. And then that leads to the conclusion that x is equal to minus 1. So we could have put sort of implies at the start of each line here, because each line implies the next line. But we're just sort of manipulating the algebra. And I would say that if you write one line after another one, it should be understood that the next line is implied by the previous line. So we don't really need to write anything else to do that. If we were going to bring in some extra piece of argument, or if there's something that's not obvious, if it's not just algebraic manipulation, then we should write something to say what we're doing, to explain what we're doing. But if one line is just leading on to the next line, you don't really need to write anything. Some people would also use 3 dots, which is sometimes used to mean therefore, and that would be another thing that some people might put at the front of each line. But again, I would say that's not really necessary. So I'm going to say here that I suggest not to use arrow to connect every line of working, but reserve it for use in more, I'm going to say more concise statements. And I'll try to give an example of what I mean in a second. Okay, so I think that's everything I want to say about if P then Q type statements. I now want to make some remarks about P if and only if Q statements. So P if and only if Q, or equivalently P if and only if Q, a double-headed arrow. And in fact, I don't really want to say too much about these because I've already made the main point in earlier lectures, which is that you should treat these separately as P implies Q and Q implies P. And if you need to prove a statement like this, that's usually the way that you want to do it. So I'm going to say here that it is usually best to treat such statements separately as P implies Q and Q implies P. And we've seen examples of proving things like this. One thing I will say, just to be wary of, because it's very easy to make a mistake, is if you've assumed P in order to prove Q, and then you change direction and assume Q, and then you're trying to prove P, it's quite easy to sort of forget that you're now no longer assuming P, and to use P, or at least to use bits of P. P may be quite a complicated combination of statements, even though you're now trying to go the other way and prove it. So it's quite easy to confuse yourself. So you almost want to just completely stop and start again when you're going the other way. Sometimes it will be the case that exactly the same argument works in reverse. And if that's the case, then you may be able to streamline things a bit and just say, we can follow through the steps of the argument backwards, and therefore Q implies P. Maybe you don't need to repeat the argument if it works exactly identically going backwards. But if you're going to do that, you just want to check that every step of your logic does work going backwards. Sometimes you'll need a completely different argument going the other way. And then you really do have to write out sort of separate proofs for the two different directions. Okay, sometimes, however, I like to read this arrow as is equivalent to, which means the same thing. And sometimes I think it may be better to read it that way. So I'll just say, sometimes it may be helpful to read these statements as P is equivalent to Q. And let me just give you an example of that. If I make the statement a function f from x to y is injective, right, that is equivalent to the statement that for every x1 and x2 in the set X, f of x1 being equal to f of x2 would imply that x1 is equal to x2. Right, and I'm going to put some brackets around here, and in fact maybe I'll even put some quotation marks to say that that's. So I'm saying that this statement, f is injective, is equivalent to this statement, that for every x1 and x2 in X, if f of x1 is equal to f of x2, then x1 is equal to x2. Right. And this is what I mean by saying that you could use arrow in more concise statements. This is a concise statement of the definition of what it means for a function f to be injective. And I'm going to come back to this. We're going to do a couple of proofs using this kind of statement. Okay, but this whole line is then a statement where I'm reading this thing as is equivalent to, and I think sometimes it's helpful to read the arrow, double-headed arrow in that way. Some of these things are a bit personal. People use this notation in slightly different ways. The last remark I want to make is about the word or. So this is a remark about the word or. And this is again just a difference between mathematical usage and English usage. If I say in English P or Q, then I will quite often really be implying that it's one or the other. So I mean P or Q, but not both. When you use or mathematically, you don't mean that. So you mean that it could be P or it could be Q, or it could be P and Q that are true. So I'm going to just say P or Q. Remember, this wedge symbol can be used to mean or. So P or Q means P is true, or Q is true, or both are true. Right, there's no suggestion that you can't have both of them. So it's not an exclusive or. Sometimes you might want to use an exclusive or. So if we do really mean the exclusive or, then personally I would just write it out. So I'd say write something like P or Q, but not both. There are some symbols that are used for exclusive or, but they're not so standard. You could do it using a combination of other symbols. So we could say P or Q, but not both. That's equivalent to, well, basically there are two options. You could have P and not have Q, or you don't have P and you do have Q. Right, so hopefully you can translate that expression there. That's saying that you have one of P or Q, but not both. Okay, so I'm going to take a pause there, and then I'm going to talk more about how we deal with quantifiers, so the for all and the there exists symbols. So this will be all about quantifiers, and I'm going to make various remarks about how to deal with these. So this is going to be remarks about the quantifiers. And I think when you're first introduced to these can be quite confusing, and there's various aspects of them and that you just need to practice using a lot before you become more fluent with it. I would say that these are most useful for giving concise statements of definitions and properties. So I'm going to say these are most useful for providing concise statements of definitions. So for example, if f is a function from x to y, then f is injective if, and I gave this definition in the last video I think as well, but I'll just write it again, if for every x1 and x2 in x, f of x1 being equal to f of x2 implies that x1 is equal to x2. So if you look back to where we defined an injective function, which was in the last lecture, I wrote out something that says the same thing as this in words, and it's perfectly fine to write it in words, but sometimes it's quite nice to have a sort of succinct expression of something in terms of symbols, and you may find that this is useful to have this when you're trying to prove things. The definition of f being surjective we could write in a similar way, so I'll say f is surjective if, so this time it would be if for every y in y there exists an x in x such that f of x is equal to that y. Right. You may notice that as I'm writing that I'm saying it, I'm saying it out loud because I'm talking to you, but even if I'm writing this myself, not to a camera, I don't say it out loud, but I do say it to myself. So I like to be able to read this thing kind of as a sentence, and that personally I'm kind of saying it as I'm writing it in order to help make sure that it makes sense. So I tend to then reread it to make sure that it makes sense. So this says for every y there is an x such that f of x is equal to y, and then I convince myself, yes, that is indeed what I meant to say. That is the definition of f being surjective. that's part of the reason why I like including this st to mean such that. But you may remember that I said some people don't include that, or some people will use a colon in place of that. I also tend to like including commas. This is totally a personal thing, but I like to include a comma where I would pause slightly when I'm reading this. And I find that helps. Okay, so those are examples of how we use quantifiers, and I'm going to show you some more examples of some proofs that involve these in the last couple of lectures. One important thing to say is that when you use a quantifier, it generally relates to a set. So here we've said for every x1 and x2 in x, and here I've said for every y in y, there exists an x in x. And it's important to specify which sets the quantifier relates to. So I'll say we should specify the set to which the quantifier relates. And so, for example, we shouldn't write something like this. For all x, x squared is greater than or equal to 0. Right? If we're working in the context of the real numbers, that might well be something that's true. And in fact, that might be an okay thing to write if it's really obvious from the context that x is a real number. But it's generally best to say that x needs to be a real number, because obviously if x is complex, which this statement allows, then this would not be true, right? And equally, x could be an emoji or something. There's nothing here to tell me that x is even any kind of number, and then this statement wouldn't even make any sense. So we should have written for every x in the real numbers, x squared is greater than or equal to 0. But there are some times when it's so obvious from the context in which we're working that the number might be a real number, for instance, that it becomes a bit kind of pedantic, and it will start making the statements really long if we keep saying what set they're in. So sometimes it's kind of it's okay not to do that. And so I'm just going to say, I think you probably will see this happening in analysis. So I'll say in analysis, we might write things like for all epsilon greater than 0, something is true. And in a statement like that, it's understood that epsilon is a real number. Right? You assume that this means epsilon is real. This kind of thing, if you haven't seen this yet, you'll be very familiar with such statements by the end of term. So I'll say in which, so we write things like this, in which it is understood that epsilon is a real number. And that's kind of accepted that that's an okay thing to do. Okay, so the next thing that I want to say is just something about how you might prove these statements. There's quite a good sort of general rule for how you should go about proving a statement that starts for all x in x. So I'm going to say, to prove a statement of the form for all x in x, something is true. So you've got to try and prove that something is true for every x. That means that you should just take an x and then try and prove that the something is true for that x. And the x that you take has got to be completely arbitrary. So the way that you start the proof is you just say, let x be a member of the set x. So I'm going to say we should start the proof with let x be in x, and then full stop. Then what we do next depends on what it is that we have to try and show. But that once we've picked our x, so once we've let x be some particular x, we then can't do anything else with it. So then we treat x as fixed for the rest of the proof. So you can't then assume that X has got any other properties or change its value. Some people think of this as like someone else is going to come along and give me an X. If my statement's got to be true for every X, then someone could throw me whatever X they like, and I've got to be able to prove that it's going to work for that X. So sometimes actually you might start the proof not with let X be in X, but you might start it as given X in X, and then you continue. But the point is that you can't make any assumptions about the X that you're dealing with. You've got to just work with the one that you're given. You'll notice that not every proof of a statement like this starts with let X be in X, but it's a good idea if you're stuck, especially, to start with that. So I'll just say the proof could also start given X in X, something that depends on what it is that you then have to do. Okay. If you're trying to prove a statement like there exists X in X such that something is true, then there isn't such a kind of hard and fast rule for how you should go about starting to do that. What you've got to try and do is to show somehow that there is an X. And it may be that you can just spot one and say, well, here is one. You just hand it to the reader and say, well, there's the proof. There it is. But typically you won't be able to do that. But you might be able to show that because of some other thing that you know, you can show that there must exist this thing somehow. But how you actually go about doing that may depend on the precise problem. Okay, the next remark I want to make is about the order of the quantifiers. So this is going to be a remark about the order of the quantifiers, which really matters. So let me give you an example. This is an example that we've seen a bit before. So suppose S is the set of Oxford students and C is the set of colleges. Then we're going to consider the following statement. So consider this statement. For all S in S, there exists a C in C such that S is a member of C. So the elements little c in the set of colleges, big C, are themselves sets of people. So I'm saying the student is a member of the college, thinking that the student is a member of that set. So this statement is saying for every student there is a college such that the student is a member of the college. So this is a true statement, expressed in a kind of mathematical language. If I change the order of the quantifiers here, so I just did them the other way around. So I said there exists a C such that, remember the such that kind of goes together with the there exists, such that for all S in S, S is in C. So now if I just read that, that's saying there exists a college such that for all students, the student is a member of the college. So this is not a true statement, because this is saying that there's some particular college such that all students are members of it. Right? So that's a different statement. And so the important thing here is that when you read any statements like these, you've got to read from left to right. And anything that you introduce can depend on things that were previously introduced, but can't depend on things that are in the future. So in this first statement, the college that's introduced here, the existence of this college, could depend on the student that came from here. So we said for any student, there is a college which may depend on the student, and indeed it does, such that the student is a member of the college. In the second statement, we're saying there is a college such that then all students are members of that college. The college can't depend on the students which have not yet been introduced. So this statement would not be true. So this first one is true, and the second one is not true. Okay, so the order in which you write these quantifiers matters. And we'll see sometimes there'll be more than two quantifiers. You may end up with long expressions that involve lots of quantifiers, and then you actually have to be really careful about it. But it's really systematic. Anything that's introduced, any element that's introduced by a quantifier can depend on things that have previously been defined, but not on things that are yet to come. We just read from left to right. Part of the reason why this can end up being a bit confusing is because the English language is not very clear about this. So for instance, in English, I could say every student is a member of a college for some college. And there it's actually not clear in what I just said whether the college needed to depend on the student or not. I said every student is a member of a college for some college. So English itself is not clear, but these mathematical statements are clear. At least they should be clear. So maybe I'll just write something so that this is on paper. We should read from left to right, and any quantifier, or any element introduced by a quantifier, any element introduced by a quantifier can depend on previously introduced elements, but not ones that are yet to be introduced. Okay, so I hope that makes sense. And then the final thing that I want to make a remark about is how we negate statements like this. So this is a remark about negation of quantifiers. Okay, so if we have a statement like the P is the statement for all x in x, some q of x holds. If I wanted to negate that statement, so that would be not P, so if this statement is not true, well then that means that there is an x for which q does not hold. So we would write that as there exists x in x such that q, maybe I'll be consistent and write that as q of x, is not true. I could have written this as not q. Okay, and if P is a statement that includes as there exists, so if it's the statement there exists x in x such that q of x holds, then when we negate that, so we do not P then, so if we don't have that there exists x in x such that q holds, that means that for every x in x, q does not hold. So the not P in that case is for all x in x, q of x is not true. Or not q, we could have said. Okay, so the rule about how you negate a statement like this is that you change the for all into a there exists, and then you negate the statement that the quantifier was relating to. And if there's a there exists, you change it into a for all. So the for alls and there exists kind of change places. This is basically a version of De Morgan's rule. Remember about how to negate statements. So maybe I'll just make the comment then that to negate a statement involving quantifiers, we change for all to there exists and vice versa, and we negate the statement to which they relate. So let me just give you an example. So actually, let's negate this statement up here, this true statement. So I'll say, e.g., the negation of this statement star is. So I'm just going to follow the rule that I just said. So I'm reading this, and I'm going to negate it. So I'm going to say, the negation is that there exists an S in S such that for every C in C, S is not in C. Okay, so this one came from this, this came from this, and this was the negation of this. Okay, then let's just read that to ourselves and check that we agree that this is saying the opposite. So this is saying there exists a student such that for every college the student is not a member of a college. So yeah, that's saying there's a student who is not a member of any college, which would be the opposite of saying for every student there is a college of which they're a member. Right? So this is fairly straightforward if you're dealing with kind of simple statements, but once we end up with longer expressions that involve more quantifiers, it's again something that can get a bit confusing. Maybe just as another example, let me go back to here. So I gave the definition here of f being surjective. So if I wanted to show that a function was not surjective, it means I need to show the negation of this. So it would mean I need to show that there exists a y such that for every x, f of x is not equal to y. So that makes sense. It means we need to find a particular y such that there's no x for which f of x is equal to y. That's the definition of the function not being surjective. Okay, so this can take a bit of practice. It may be that what I've said here makes complete sense to you. It may be that it all sounds really confusing. It is like a different language, and I think it does take a while to get used to doing this kind of thing, but you'll probably find that in a few weeks' time you're completely fluent once you've practiced it. You may well find that it's actually worthwhile re-watching this video, this particular video where I've been talking about sort of logic and quantifiers. You may find it's worth re-watching that at some point later in term once you've had more practice doing this kind of thing yourself. But you may think that you're completely happy with it by then, in which case that's great. So let me just remind you what we've done here. So we've talked a bit about using quantifiers. We've remembered that we need to specify the set that the elements are in. We've talked about how we can prove these statements, and in particular, if we're trying to prove something that starts for all, then we should start with let x be in x. We've mentioned that the order of the quantifiers matters, and then we've talked a bit about how to negate a statement that involves quantifiers.